All right, so this is part two of our. Oh, sorry. This is part two of our well, it's our second video, and this will be determining the pressure gradient using the fluent results with the theory taught in class. So for this, we're going to be using the Navier-Stokes equation, and in addition, we're going to need our u at 0, which is -2, 0 being the point. And then two other points for that, we're going to use u at the other wall, which is 3, and then our maximum u, which is 7.3222 at this point here. And then we'll also need the viscosity, which we chose as 1.5 e -5. And that'll be enough for us to solve for our pressure gradient. So starting with the Navier-Stokes equation, we want to first expand it out. We break open that material derivative and that del section there. And then from that, we're going to simplify down. So because it's steady, we don't have to worry about our du dt. Fully developed, there's no, the flow isn't changing with x. 1d, no z, and no g, so we can cross out that v, w, second derivative u with respect to x, second derivative u with respect to z, and then that gravity term. And what that becomes is this here. And at least, see, actually, technically we want to have it like this, because we're going to be integrating with respect to velocity there. So the next step is we're going to integrate that twice with respect to velocity. It's pretty simple, and that just leaves us with this here. Unfortunately, it leaves us with two constants. And those were those points that we described earlier come in. First, we're going to plug in our point at 0, where we had our velocity of -2. Because we have our y values, we can cancel those first two terms and just have c2 equals to -2. Then we plug in a second point. For that, we're going to use the other wall, which for us was at 0.005. And that is a velocity of 3. We plug that in and get our c1. And then for our third point, we just did our max velocity here. And once we plug that in, we can just do the algebra, plug in our mu, and we get this equation here. Now that's super big, so we just did it in Desmos, which leaves us with -31.6 pascals per meter. And that is how we determine the pressure gradient using the fluent results with the theory taught in class.